So let me now talk about properties of discrete time Fourier transform, because most of these properties are similar to many of the properties we talked about for the continuous Fourier series as well as for the continuous time Fourier transform. So we're not going to spend a lot of time on these properties, but nevertheless, let me just give you a quick review. The first property is periodicity, and that's a property that is different than the continuous time Fourier transform in the sense that as opposed to the continuous time Fourier transform, the discrete time Fourier transform is actually periodic in the frequency domain with a period of 2 pi. And that's actually one of the reasons why we use a notation x and e raised to power j omega, where this e raised to power j omega, if you recall, represents the equation of a circle. So e raised to power j theta represents a circle in which theta is modulo 2 pi, and omega therefore is modulo 2 pi here as well, which it actually is in the frequency domain. So any frequency which is omega is exactly the same as frequency which is omega plus 2 pi, because omega is going to go around the circle and wrap around and come about, and plus 2 pi is going to get you a point, which once again is omega. So that's one of the reasons why we use this notation e raised by j omega to represent the fact that the frequencies lie on a circle. And the period, of course, is 2 pi. Linearity is very, very similar. I don't need to say a lot about this. Superposition in the time domain is equivalent to superposition in the frequency domain. All right, that's all I'm going to say. The time and frequency shifting, if I shift in time, that's equivalent to multiplication in the frequency domain or the Fourier domain by an exponential. On the other hand, multiplication with an exponential in the time domain is equivalent to shifting in the frequency. And of course, you once again see that there's a duality here. Shifting in the time domain is equal to multiplication with an exponential. On the other hand, shifting in the frequency domain is equivalent to multiplication in the with an exponential in the time domain. So there's duality here. There's a neat application that is a result of this frequency shifting property, and so let me just talk about a simple example to discuss that. So I am interested in finding what the Fourier transform of -1 raised to power n times x of n is. So in other words, I need to figure out what does multiplication with -1 raised to power n in the time domain does to a signal. What does it do? And in order to answer this question, I observe that -1 raised to power n is actually e raised to power j pi n. And so omega naught, so I can then use the frequency shifting property with omega naught equals pi to conclude that the Fourier transform of this signal is actually the Fourier transform of x, except that it's going to be shifted by pi. So if I give you a visual interpretation of what's actually going on, so if there's an x of e raised to power j omega here, and let's assume that x of e raised to power j omega was a low pass signal. In other words, a majority of its energy, or actually all of this energy in the signal, resided in the low frequency component. So the Fourier transform is 0 at pi, and it's non-zero around the frequency of 0. And since, of course, this is periodic, the Fourier transform is periodic, I must have a copy here, and I must have a copy at -2 pi as well, which is exactly the same as copy as I have at 0. And what happens after I multiply with -1 raised to power n? So I get a Fourier transform, which is x of e raised to power j omega minus pi, and all that's going to happen is that the copy that was at the frequency of 0 is now going to reside at a frequency of pi. The copy at which was -2 pi is now going to reside at the frequency of -pi. And that, of course, should be no other way, because I know that the Fourier transform is periodic. So anything that's there at the pi, we must have a periodic copy at -pi as well, because the difference between these two frequencies is 2 pi. So what we observe is that it's multiplying by -1 raised to power n in the time domain with the discrete time signal. What it does is it transforms a low frequency signal to a completely high frequency signal. And as you recall, pi is the highest frequency that you can have in the discrete time. So the low frequency signal, once again, is converted to a high frequency signal. Now, the question I want you to try to think on your own is, what if the actual x of n was a high frequency signal? And then what you should be able to figure out is that -1 raised to power n multiplication with that is just going to transform that high frequency signal back into a low frequency signal again. So that's something you can try to think on your own. Now, there are other properties that are very, very similar to the ones that we've talked about earlier in the continuous time case. So I'm not going to spend a lot of time. The time reversal, if you flip the signal in the time domain, then the frequency domain, the signal is flipped as well. Conjugation, the Fourier transform x conjugate of n is x conjugate of e raised by minus j omega. So there's flipping in the frequency domain, and then there's conjugation in the frequency domain as well. And this then results, along with time reversal, results in all of those conjugate symmetry properties that the Fourier transform of a real signal is going to be conjugate symmetric. The Fourier transform of a real and even signal is going to be real, and so on and so forth. Multiplication property is slightly different, but nevertheless, I'm not going to talk about the proof of this. If I multiply two discrete time signals in the time domain. So if you recall, in the continuous time case, what happened was multiplication in the time domain resulted in a convolution, scaled convolution in the frequency domain. What you have here in the discrete time case is almost similar, except that the integration limits are now over an interval of 2 pi. So this is not convolution as we're familiar with, except that this convolution is over a finite interval. And this is actually called periodic convolution as well. And that's all I'm going to say about this. So this is actually called periodic convolution, sometimes also called circular convolution. Okay, parseval relation, once again, if you compute the energies, remember, so this thing here is the energy in the time domain. And if I were to compute the energy in the time domain, that would be the same as, so if I were to compute the energy in the time domain, I could just use the Fourier transform and compute it in the Fourier domain as well by just taking the Fourier transform over one period of 2 pi, taking the absolute value, squaring it up, and just finding the area in the curve of that resultant signal in the frequency domain, and just scaling by 2 pi. And that's why, because I obtain the energy by integrating this in the frequency, this times the frequency gives me a unit of energy. That's why this term here, which is x of e raised to power j omega absolute square, this is also sometimes called the energy spectrum density. And so therefore this thing here tells you at a particular frequency omega, this tells you what the energy density is in the spectrum domain at that particular frequency. And once again, the reason why it's called the density is because if you multiply this with a unit of frequency, which is equal to spectrum, you get units of energy. And therefore the units for this must be energy per frequency, and that's why it's called the energy spectrum density. And finally, the last property I'm going to talk about in this particular module is the differentiation in the frequency domain. So the question is, if I differentiate in the frequency domain, what happens in the time domain? In other words, if I find the derivative in the frequency domain, what is the inverse Fourier transform corresponding to this frequency domain transform? In order to do this, let me just use this this Fourier transform relationship or the analysis equation, and just differentiate both sides here and here with respect to omega. So the derivative of this with respect to omega is therefore equal to summation because the derivative is linear, it can go inside the summation minus infinity to infinity. X of n is a constant as far as omega is concerned. And then all I do is I just differentiate e raised to the minus j omega n with respect to omega. So this is just e raised to the minus j omega n times minus j times n. And let me just rearrange the terms a little bit. So this is j can come out of the summation. So this is n going from minus infinity to plus infinity. N can go here, n times x of n, e raised to the minus j omega n. And if I multiply both sides with minus j, so what I get is actually, so let me just multiply both sides with j. So this is j times d by d omega x of e raised to the minus e raised by j omega. So this is e raised to power j omega is equal to minus j times j is plus 1, and therefore this is n equals minus infinity to plus infinity n times x of n e raised to power minus j omega n. And from here, what I conclude is that this actually is the Fourier transform of, because this is just the Fourier transform relationship. So this is the Fourier transform of this thing here, which is inside. So the conclusion is that the Fourier transform of n times x of n is equal to j times d by d omega x of e raised to power